Section 11.3, Electric Field and Electric Field Intensity. This section introduces the concept of the electric field as the mechanism by which electrostatic forces are transmitted. Definition of electric field. While Coulomb's law describes the electrostatic force directly, field theory posits that the force of attraction or repulsion is transmitted from one charged body to another through a region called the electrostatic field. The electric field is defined as the region or space around a charged body in which another charged body can experience a force of attraction or repulsion. Source charge and test charge. Source charge, Q. This is the charge that produces the electric field. It has a considerable electric field around it and may be positive or negative. Test charge, Q naught. This is a point charge used to determine the strength of the field. It has a negligible field and is always considered a unit positive charge. It is assumed that the test charge moves in the field without disturbing the field of the source charge. Electric field intensity, or electric field strength. The strength of the electric field at any point is called the electric field intensity. Definition. Electric field intensity, represented by capital E, is defined as the force exerted per unit positive charge. Mathematical expression, E equals F divided by Q naught. Equation 11.11, where F is the electrostatic force exerted on the test charge Q naught. Vector quantity. Electric field intensity is a vector quantity possessing both magnitude and direction. Direction. The direction of the electric intensity is the same as the direction of the force exerted on the positive test charge. It is directed outwards from a positive source charge. It is directed inwards for a negative source charge. SI unit. The SI unit of electric intensity is Newton per Coulomb. Section 11.4. Electric intensity. Due to a point charge. This section derives the formula for calculating the magnitude and direction of the electric field intensity produced by a single source charge at a given distance. Derivation. To determine the strength of the electric field at a point P located at a distance ER from a source charge Q, a test charge Q naught is placed at that point. Force calculation. According to Coulomb's law, the electrostatic force F between the source charge Q and the test charge Q, naught separated by distance r, is given by F equals 1 over 4 pi epsilon naught multiplied by Q times Q naught divided by r squared. Electric intensity calculation. By definition, electric intensity E is the force per unit test charge. That is, E equals F divided by Q naught. Substituting the expression for F, we get E equals 1 over 4 pi epsilon naught multiplied by QQ divided by r squared. The test charge Q naught cancels out, resulting in the magnitude of electric intensity. E equals 1 over 4 pi epsilon naught multiplied by QQ divided by r squared. Equation 11.12. Note: 1 over 4 pi epsilon naught is sometimes represented by the Coulomb constant K. Vector form. Since electric intensity is a vector quantity, its direction is the same as the force, along the unit vector EER hat. Therefore, E equals 1 over 4 pi epsilon naught multiplied by Q divided by r squared multiplied by r hat. Equation 11.13. Dependence of electric intensity. The equations for electric intensity demonstrate that it depends upon the magnitude of the point charge Q, the distance r, and the medium in which the charges are placed. Example. Calculation. Example 11.3. Find the resultant electric field intensity at a point P positioned between two charges. Q1 equals 15 times 10 to the power of negative 9 coulombs, and Q2 equals 30 times 10 to the power of negative 9 coulombs. They are separated by 6 centimeters. Point P is 2 centimeters from Q1 and 4 centimeters from Q2. Electric intensity due to Q1, E1 equals K times Q1 divided by R1 squared. E1 equals 9 times 10 to the power 9. multiplied by 15 times 10 to the power negative 19, divided by 0.02 squared. E1 equals 3.37, 5 times 10 to the power 5 newtons per coulomb. Electric intensity due to Q2. E2 equals K times Q2 divided by R2 squared. E2 equals 9 times 10 to the power 9, multiplied by 30 times 10 to the power negative. 9 divided by 0.04 squared. IA2 equals 1.69 times 10 to the power 5 newtons per coulomb. Resultant intensity, E. Since both charges are positive, the resultant intensity is the difference between E1 and E2. E equals E1 minus E2. E equals 3.375 times 10 to the power 5 minus 1.69 times 10 to the power of 5. E equals 1.685 times 10 to the power 5 newtons per coulomb. The resultant electric field is directed towards the larger charge, Q2,